This is 3.8 times 10 to the 27th joules of energy per second. How much energy is produced in a year? Note, a year is approximately 31 million seconds. If I know how much is produced in 1 second, and I know how many seconds are produced in a year, or how many seconds are in a year, all I have to do to figure out how much energy is produced is multiply those two values together. The tricky part is, in order to do that, they both need to be in the same format. So I have 3.8 times 10 to the 27th, and that needs to be multiplied by 3.1, because 3.1 is between 1 and 10, times 10 to the 1, 2, 3, 4, 5, 6, 7th. When multiplying, in scientific notation, we multiply the numbers out front together. So we will have 3.8 times 3.1, and we multiply the powers of 10 together. When you have a base that is the same and they're being multiplied, we can add those exponents. So now we have 3.8 times 3.1 times 10, and then all we have to do is add the 27 and the 7, which gives us 34. 3.8 times 3.1 is 11.78, but we're not in scientific notation yet because 11 is not between 1 and 10. It should say 1.178 times 10 to something. For this one, I need it to be the same amount of times to move the decimal. So if I went backwards, I need to add 1 to the count. So it would say 35. If I were to move my decimal forward, then I have to go 1 less when I'm moving in the end. So then I could go back down to 33, but this time I did move forward, so I have 1 more to do. And these are in joules. It's a unit for energy. Number 2. On average, Mercury is about 57 million kilometers from the sun, whereas Neptune is about 4.5 times 10 to the 9th kilometers from the sun. What is the difference? Difference, that keyword means subtract, between Mercury and Neptune's distance from the sun. The easiest way to do this is when they're in the same format. So for Mercury, those exponents need to be the same. So I'm going to change this one to be something times 10 to the 7th. I've decreased my exponent by 2, which means I have to move 2 less spaces. So I've already got 2 spaces there. Then I need to subtract 5.7 times 10 to the 7th. Remember, when we subtract, we leave the exponent, so it's going to come out to something times 10 to the 7th. And we subtract the numbers out front. This is going to give us 444.3. But it's not in scientific notation. I want 4.4, so that way it's still between 1 and 10. And since I went backwards and made my number smaller, I need to add 2 to my exponent. 3. The mass of Earth is approximately 5.9 times 10 to the 24th, and the mass of Venus is approximately 4.9 times 10 to the 24th. Find their combined mass. Combined means add. So 5.9 plus the 4.91. Since they already have the same exponent, we just add the numbers out front. 5.9 and 4.9 come out to 10.8, and we leave the exponent. But it's not in scientific notation. We've got to change it to 1.08. I moved backwards, so I add 1 to my exponent. B, given the mass of the sun, how many Venuses and Earths would it take to equal the mass of the sun? So here's where we're going to divide 1.9 times 10 to the 30th by the Venuses and Earths. Remember, these pieces get divided, and with these ones, when we divide like bases, the exponents get subtracted. So our answer will be times 10 to the 5th, because 30 minus 25 gives us 5. Dividing the 1.9 and 1.08, we get about 1.795. You could also write 1.8 times 10 to the 5th, and this is Venuses and Earths.